All right, pre-calc kids, we are going to get started on section 3.3 here, Introduction to Logarithmic Functions. Now, we've just spent some time talking about exponentials, and you can see the exponential graph there in the blue. F of x equals 2 to the x, or y equals 2 to the x. We'll spend some time in class tomorrow talking more about what inverses are. But to give you a brief overview, an inverse is something or is a reflection over the line y equals x. So you can see that line going right through the middle here, y equals x, and it flips the values. So if you kind of turn the screen, you can see that reflection. Since it changes the x and y values, we can write our inverse equation with the x by itself and the y as the exponent. Since in math we like to talk about our dependent variable, our y variable, being isolated, we need some way to solve this equation for y, to get y by itself. So we had to come up with some type of inverse operation. We had to call it something. And so that's where the logarithm comes in. When we solve for y, we get the equation y equals log, and then we call that base 2 of x. So it looks like a little subscript. And I know it looks funny, but just think about how funny a square root looked when we first started working with those. And a square root undoes a square. It is the inverse of a square. A log is the inverse of an exponent. So again, more on that tomorrow. For our first set of examples, we're just going to evaluate some basic logarithms, and these are doable without the calculator. And I'm going to go back to the rule that I was talking about on the last slide. I used the example of 2 to the x, and I'm just going to kind of call our base b, as we have been doing with our exponentials. And so if I have b to the y power, that equals x, so that's my inverse function, flipping the x and y from the exponential. We know that the way to solve for y is to take log base b of x equal to y. So I'm going to use this to solve these problems. In this first one, log base 2 of 8. That's how we say that, log base 2 of 8. 2 is my b, my base, and 8 would be my x value here. So I'm asking myself, if I look then over at this version of the equation, 2 to what power gives me 8? And so you just need to think to yourself, and we know that we can come up with the answer of 3. And so we're going to do that for all of these. 3 to what power gives us the square root of 3? We know that the square root is the fractional exponent 1/2. I'm going to zoom in a little bit here. All right, this next one, log base 5 of 1/25. So 5 to what power gives us 1 over 25? Well, we know that 5 squared is 25. And in order to get something into the denominator, that means we need to have a negative exponent. So 5 to the negative 2 will give us 1 over 25. 4 to what power gives me 1? Oh, yep, 4 to what power gives me 1? I wrote the 0 in there already, but we know that anything to the 0 power is 1. 7 to what power is 7? That answer's got to be 1. And then I actually am going to rewrite this last one. I want it to say log base 2 of negative 8. I had a little typo there when I put that together. So for this one, 2 to what power is negative 8? So I want you to think back to the exponential graphs that we've looked at. We know that there is a horizontal asymptote at y equals 0 if there isn't a vertical shift. And so we've had a discussion about how there's no solution to this problem. And so we get that type of answer from time to time with logarithms, as we do with anything else. What I would like you to do as part of your notes in your homework here is finish working on, well, let's see, there we go. Finish working on these problems and bring them to class so that we can discuss. Based on what we did in example 1, let's just talk about a few of the basic properties of logarithms, things that are always going to be true. If we look at just the general base b as we've been using, if we take b to some power, how do we get b? We know that that exponent must be 1. So we saw that in the example log base 7 of 7. If we take b to some power, how do we get 1? We must have an exponent of 0. Now, we know that the exception to that rule is 0 to the 0 power, but if you look at the top of the screen here, we've got some constraints on b. It has to be greater than 0, so it can't be equal to 0, so that takes care of that undefined case. And then also, we don't want b to be equal to 1, just like it can't be equal to 1 when we're talking about exponentials, because then it would not be growing at any rate, it would be constant. Moving along, for these next two, b to what power gives me b to the y? That exponent must be y. And so it's kind of like they don't really cancel each other out, but they create that common base. It's similar in this next one, b to the power of log base b to the x. That just gives us x. And we'll talk about that one more in class as well. You're going to use these properties when you have to do some evaluating. Maybe you don't have your calculator available. You want to know when you get 1, when you get 0, and so forth and so on. When working with logarithms, you won't always see that subscript, that base. When it's not there, it's assumed that it's 10. Kind of like when you don't see an exponent, you assume it's 1, or when you don't see a coefficient, you assume it's 1. So when we're looking at this first problem, log of 1, we can assume that that means 10. Oh, can't really see that. Let's make it a little darker. There we go. We can assume that that's 10 to some power gives us 1. So as we've discussed, that'll be 0. Log of 10, that'll be 10 to what power gives us 10. So our answer is 1. In the next one, 10 to what power gives us 10 to the y? That's got to be y. And like we saw on the last page, this one's going to give us y as well. It's kind of like those cancel each other out. We also have something called the natural logarithm. The natural logarithm uses that ln. We worked a little bit with e in the last section as well. So the base of e, that number 2.718, blah, 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 that just happens to come up and be very useful in a lot of practical applications in finance, etc. So it is practical to create some models that have a base of a natural log versus a common log. So we want to be able to work with these as well. To distinguish between the natural log and the common log, we used ln, n being for natural. And so now you're going to pretend you see the little subscript of e in between there. So e to what power gives me 1? That would be 0. E to what power gives us e? That would be 1. And just like we've seen on the other screen, we're going to get y and y for each of these for similar reasons. With that said, I'd also like you to work through these sets of problems as part of your homework. See what answers you can come up with, and we will discuss them in class. All right, let's get a little calculator practice in here. When you see, again, the log without any base there, it's assumed that it's 10, and that's the log that you see on your calculator. So if you just practice with me here, typing in log of 34.5, you should get 1.54. When you type in log of 0.43, you're going to get negative 0.37. I want you to think about why we might get a negative answer here. Remember that we can change this to an exponential to think about a solution. So that would mean we take 10 to some power gives us 0.43. Well, if we're going to raise a number like 10 to some exponent, that in order to get a number less than 1, we're going to have a negative exponent. We saw that in our very first set of examples. 5 to the negative 2 gives us 1 over 25. It's a similar situation here. So even though you wouldn't have known that the negative 0.37, we could have guessed that it would be negative just based on what we're taking the log of and looking at that exponential form. For this next one, if you type it in your calculator, it's going to give you an error. There's nothing wrong with your calculator. That's what it should be doing. That means there's no solution. And again, I want you to think about why. It's 10 to some power gives me negative 3. When you look at the graph of an exponential, 10 to the x, we're never going to get negative 3 as a y value because of that horizontal asymptote at y equals 0. So that's why the log of a negative is going to be no solution. Similar story for the natural logs over here, and I'm just going to jot down the answers and again ask you to check them. We get another negative in this second one because what we're taking the log of is less than 1. And again, in the last, natural log of negative 5, even though we have a different base, when we take e to some number, e is just like 2.7, guys, we're not going to get negative 5. So there's no solution for this one as well. The last set of problems for this page ask us to solve by changing to exponential form. So now you'll notice that the x is in a different spot. And we are given what the log is equal to. So we're going to use the same idea that we have the entire time, but now you're going to find that instead of finding the exponent, we're going to be finding what it equals. So in this first one, I'm thinking of this like 10 to the third is x. Okay, so I take my base of my log, what I have on to the power of what I have on the other side of my equal sign equals what I'm taking the log of. And we can compute 10 to the third. That's 1,000. For the next one, I'm going to say that 2 to the fifth power is x. And we know 2 to the fifth is 32. As we move on, we're back to the common base. So we're back to 10 to the exponent of negative 1 is what our x value is. And I'm just going to leave that in fraction form here, 1/10. And lastly, 4 to the negative 2 is x. And so that's 1 over 16. The others with the natural logs are going to work the same, except now you don't have to pay any attention to what the bases are, because they're all going to be e. The only time we will ever use ln is when we're using the base of the natural log. So for these, you're going to want your calculator. This is going to say e to the first power is x. And so if you type that in, you're going to get about 2.72. E squared is x. That should give you about 7.39. E to the negative 3. So we know that that would be 1 over e to the third. There we go. That's about 0.05. And lastly, e to the 0.42 is x. That should give you about 1.52. And that is all I have for you tonight.